Hello, this is Justin Hickman. I'm with Birdispan. It is Thursday, April 6th, and today I'm catching up where we left off last week with the in-browser database. I'm using GWT. Um, I moved my mic, so hopefully this will work a little bit better than it did last week. But let me go ahead and switch over. Today, let's summarize what we did last week. Last week we created this GWTDB. Eventually, these will probably be code generated. So there's going to be an annotation processor that can generate using some sort of generics to identify the type of document that's going to actually go into the store, the database, so to speak. Maybe eventually this will support going over the wire or being able to support a browser IndexedDB or something like that. But right now we're only focused on the memory side of it. So just holding it into memory. And I kind of wanted to be able to do quick searches, be able to find data relatively quickly based upon indexes. Not entirely sure how the indexes are going to play out, but here we can create the other database, create some named properties. That way we can actually refer to them by name rather than having to pass a lambda every single time. We started playing around with creating index, at least for the API of it, what it could actually look like. This could be transferred over the wire. Give it a name. And since create index returns a promise, we can do something once that has completed. And here we just create a document, add it using post. This will actually add the item with an ID auto-generated from the other database. But you can also set your own ID on an object, and then you can use put, and it'll be able to use the ID that's already there. If you didn't have an ID and you called put on an object, it'll complain saying that there's no ID present. Maybe eventually we'll be able to look at things like doing differences between bean instances. That way we can actually have historical data. Might be able to do it now. I am not entirely sure how we're going to do that. But I want to play around. You probably saw whenever I pulled up my my desktop that I have a B tree little test bed. This is kind of interesting. So B tree is a little bit different than a binary tree. I'm not going to go into the full explanation of how this works, but basically similar with a binary tree, it allows you to quickly locate objects in your tree. But binary trees by nature could have a worst case scenario where it's completely unbalanced and based upon the order of adding items to the other tree, it will basically be a line all the way down. So searching would be big O of in instead of big O of log in. So with a B tree, they self-balance. So if I add like 50 here, let's see, animation speed. Can I zoom that in? Let's do 500 by 500. That did not. That just changed the canvas size. Didn't actually change my visualization here. easier. All right, so you can see that it added 50. If I added 75, this will basically just add it to the same node as a different key, I guess. So this, we have a max degree equals 3, so that means that at most each one of these nodes will only have a maximum of 3 items in it. So if we were to add 1, that'll add it in degree. I guess what it does is as soon as it gets to that point, it'll split off. This works a little different than some of the demos that I was seeing yesterday whenever I was playing around with this. So let's add a 60. Oops, did do that. And that adds it there. Can't do anything with that. 55. So that promotes the 60 up here. And basically, inserts are a little bit more expensive because you are restructuring the table. But the searches are going to be very, very quick. I don't really have a lot of data in here, but if I do like 75, you can see that it's able to find it rather quickly instead of having to look at every single key. So basically, if you look at this in terms of ordering, whenever I look at the root node and I see the first key has 50 in it, if the number that I'm looking for is less than 50, I would look at the very first child, which is going to be 1 in this particular case. If I insert another and we have 2, both of those are less than 50, so they are in this node down here. So it does make it quite a bit quicker to locate your objects. If I add a 10, this will split this one off and move the 2 up there. And notice that once that became 3 items, it pushed another height to the other tree. So here we have 1, 2, 3, or 1, 2, 10, 50, 55, 60, 75. So it's always going to be in order, but it's just a matter of how it's going to be connected in the other tree. All right, so I kind of want to implement this in a GWT safe way. Obviously, we're not going to have the other pretty animations. But we will need to have some sort of B tree. I could probably use some of the tree functionality in core Java, but it's more fun to implement something new. So if I create a new package, I should probably name it like B tree. All right, so first thing that I'm going to do, let's create a node. And a node is basically a representation of one of these boxes. So if I add 51 in here, it should just add it to that one. There we go. So this is a node. So it contains multiple keys, and it also contains possible children. So you can see that this node has 2 children. Children. And we can just make a determination of whether or not it's a leaf node. Not with that attitude. I must have missed where that was. So let's go ahead and create something in here. And our keys, I mean, looking at this, if I were to insert like ABC, it is able to compare these. They are comparable. So I'm wondering if my keys should be comparable. I mean, that would definitely make it easier to figure out which ones are greater than or less than. So if I have a private, I don't know if I should do an array or a list. Let's just do an array list of comparable anything for now. All right, and private final. Children. Wonder, did my chat show up? Yeah, it does show up. Okay, cool. So I added a little box there, and I'm hoping that actually goes away. Not sure how long it'll be there for. Oh, there it goes. That way, any kind of chat in Twitch, we'll be able to still see it on the YouTube side, so that it's not completely out of context for anybody watching on YouTube. All right, private boolean leaf. By default, it's false. So let's create a constructor. Node. Might make this final too. I am not sure if I need these as final or not. And that is basically it for this particular thing. So let's go ahead and create a B tree class. So let's pull our node over here. Yeah, let's swap that. So node over here and B tree over here. Only because where my camera is positioned. I want the code to be able to be seen. All right, so the first thing that I probably want to be able to do is insert or add a new node, right? So I'm wondering. Public void add node. Obviously, you can't insert in any particular position because the B tree will be responsible for all of the self-balancing. So the thing that we need to be able to do is figure out how many degrees we want. I'm not entirely sure. Private int degree. Let's do 3 for now, only because it's easier. But definitely, whenever we are, because of the fact that rebalancing the tree is such an expensive operation, we probably want this to be closer to like 500 or basically whatever our quote-unquote page size is. Since this was originated from database indexing, basically you have a page of data. So if we did like 500, then we can insert up to 500 into a single node. See, that's confusing now. Probably need to change terminology, but let me just stick with 3 for now. Wondering if I can easily make a to string on this that would be able to visually display all of my children and hierarchy. But let's go ahead and look at this insert again. Probably will make the getters and setters on this side. And not setters, obviously. Really don't like people on the outside mutating, but maybe make these package private for now. Just to protect it a little bit, because most likely this B tree is going to be modifying the nodes directly. Alright. So what has to happen with the insert? So if the we need a root, obviously. So private node root. And I should probably just do new node true, because the root, gotta have a root, and it's just going to be an empty node. No keys, no children, and it is going to be the leaf. This could probably be set in a constructor arg, but I'm not going to worry about that too much right now. So if the root get keys is equal to 2 times the degree plus 1. Let's figure this out. So let's ignore this one for now. Basically, we need to be able to check to see if the root is full, and be able to insert appropriately. But I also need to be able to insert if the node is empty, doesn't have any keys. So if I were to do that, I'm going to do insert non-full, and we're going to pass it the root and the node. No. Yeah. No. I think what I want to do is data. So we add dv data. So this node is just going to be private to the B tree. The more I'm thinking about it, because I don't need to expose any of this stuff, so that might be fine. So let's insert non-full root, and this is assuming an else here. Gotta find out if the root is full, and be able to figure out if I need to create a new root, things like that. So if it's non-full, void insert non-full into whatever node. And then just call that X for now, because I'm not entirely sure what we're doing on that. And let's just do D for data. So if X is a leaf, we need to find the correct spot in the leaf to insert the key. All right, so what we can do here, no, int I is greater than or equal to 0. And get keys, get at I. See, this is where we need to use this as a comparable. These are keys. So like in here, these are going to be keys. Of course, they're going to be something connected to it, but the keys themselves have to be comparable. So I kind of need this to be a K for a key. I mean, right now we're just doing a educational academic approach to creating a B tree. I've never actually created one of these before, so I'm having to think through some of the issues. So K compared to, of course, we got to figure out what to do with null. Keys are comparable. Probably need to be a comparable of the same thing. And compare to, that returns an int. And I believe if it's less than 0, means that this one is less than, okay, is that right? Negative, integer, 0, or positive. This object is less than, okay, so this object would be less than this one. So I don't know why I put declaration there. So I is going to be, next I get keys, length, or size. Sorry, it's a list, not an array. This one. I might have to pass this in to node. generic. And it did not work. Will that return? Shouldn't comparables be comparable to comparables? Okay, extends comparable. Negative K. Oh, this is where it's going to kill me with the generics. Trying to compare these. It should be a list of K. It's probably because of the comparable up here. Another type in here. I'm probably really messing this up. I don't think this is going to help any. Yeah. Yeah, I didn't think so. Okay, it's not updated. Yeah, that's fine. Eventually I will. Type T. So I might be mistaken on that. It's been a while since I've looked at this. Ugh. Can't stand generics at times. So K is the comparable to T. Oh, so I need a T here. That's not good. That is not what I was wanting. Basically, I just need two. This would be T, right? The keys would be of. Yeah, I completely messed this up. So if I were to have integer, for example, the keys are going to be integer, right? It's also comparable. I wonder if I should make the other. No, that doesn't make any sense. That's right. Let's try this one out. So K extends comparable of K. So the key is comparable to other keys of its same type. Seems correct to me. Ha! There we go. Knew I was going to get it at some point. All right, so let's just grab that. Yeah. That's fine. I'm a big fan of getting the value multiple times. I could probably make that a little bit cleaner later. So if it's a leaf node, just grab the keys, and I'm going to iterate from one less than basically the end of the list, and compare them. So while I is greater than or equal to 0, K compared to keys at K is less than 0, meaning that it's less than. So I probably need to append a null here. So that'll add a null to the very end. So I'm basically going to left shift or right shift until there's an insert point. Yeah, we can. We probably need a unit test just to verify all of this stuff. Get keys. We want to set I+1 to next up. Get keys. Get I. So that you have one before it. Yeah, this seems rather stupid. There's a lot of movement here whenever all I should be doing is inserting into it. I mean, it probably makes sense if it's a language with arrays. This is a really stupid way to do this. And minus minus. Yeah, I should probably create a toString for this. I'm not sure the best approach for that. Let's go ahead and create a test. Test. Oh, JUnit 3. This is 3. Alright. So if I have a B tree of integer, tree dot add 5, 2, add 8. See what that does. I mean, obviously it's not going to print anything, but I just want to see if there's any kind of errors. And there is. Cannot read field value because another integer is null. What? Oh, it's because that's null. I wonder if these should be pre-created. All right, so let's take a look at this a little bit closer. So we're assuming that this is a non-full node. Here. Hold that thought for a second. So if it's not a leaf, I could probably... Well, this is going to be a leaf, but if it's not a leaf, there's going to be a different logic for this. Probably pull that out. Yeah, that's a really stupid way to do that. Basically, I just need to find the index. Blah, blah, blah. So the keys, if keys is empty, that'll be -1, so that won't even go through that loop. Ow, I need to get rid of this part because we're not left shifting anymore. Alright. So, what I want to do, instead of toString, might get confusing. I would rather just see the data. Tree. No, I just called it a tree. But all I'm going to do is put a breakpoint here. Maybe. There we go. Then debug this, and I just want to see what the data structure looks like. All right. So we have the tree, we have a root, and it contains 2, 5, 8, and 10. That is ordered. Okay. Obviously, we're exceeding the bounds of how many keys can go into a single node because I implemented this to be 3 as the other number of degrees. Or, I don't know if that's the right term for that. Public B tree. B tree. Okay. And that's where this is going to come into play. But so far, this is actually at least sorting appropriately. Yeah, 2, 5, 8, 10. Let's continue that. Let's go back to our test. Oh, this is our test. Tree add -5. So it should be -5, 2, 5, 8, and 10. Yeah, there we go. Cool, cool, cool. All right, so that's not needed. That's not needed. So that looks like will work. So this will use the comparator to actually do the other comparison. I mean, this does assume that it's a comparable. We could change the interface later to include our own comparator rather than having to use comparable, because not every data type or bean is going to have a implement comparable. All right. So now, since this is not a leaf node, which we're not even into yet, so let's go back up to the add and figure out how that's going to work. All right. I'm not sure why I'm multiplying by 2. So if I have 3, let's just do degree -1. I don't know what the other term would be for that. This just shows maximum degree, but it's apparently not inclusive. Oh, apparently it deletes my stuff whenever I do that. So if I add a few numbers in here, it should go up to 3 in there, but then 4 is whenever it splits. Okay. So it's not inclusive in this example. So if the root key size equals degree of 1, let's just throw a new runtime exception. And let's just make sure we actually hit it whenever we try to insert the other 4th. Yeah, there we go. There we go. So we have 2 and 5, and it's like, hey, our degree is 3. We need to do something different. So this is where we're going to basically. Oh, thanks for the follow. Voxter Karyaja? Sorry about butchering your name. Iriaja? Alright. So then, basically, this means that the other root is full. Hey, not much. I am just creating a B tree implementation. Just playing around right now. I'm trying to see if this could work for like a in-browser database using Java. Have you ever used the fake REST API JSON server? I have in the past. I've actually used some fake servers for like SOAP back in the day. They were kind of interesting, where you basically create some sort of state on that, mainly for unit testing, right? Are we talking about the same thing? I can't remember the name of the software that I used, but it was very convenient for web services. I think they also did JSON stuff. How I can make a search box where you can search different products that the web have. Are you talking about on your own website, or are you talking about like some sort of Google search for products out on the other web? Google search bar for the products that are in my web, like in your application. I know that at least the old GWT project did this. So if I take a look at the GWT project, the search up here, if I type in like UI binder, notice that it goes to Google because all the ads at the very top, but all of the other results are going to be limited to your site. You can always have it do that. I don't know off the top of my head the steps to be able to do that, but you should be able to quickly figure it out. Yeah, like here. This is probably exactly what you need. That'll allow you to create a search index for your website, and Google will be able to traverse it, be able to index it appropriately, and then you would be able to use that. I mean, it's not necessarily like a JSON server or anything like that, but it allows it to be spidered for indexing. All right. So what I'm doing here, so the root is full. create a new node. Tree height grows by 1, so I create a new root node. I set this root to the new root. And for the new root, I'm going to add the old root as the only child. And I want to split the other child. New split child. The new root. And insert not full new root. All right, so let's take a look at this new function that we're creating, split child. There, public. This is private void split child, and that is going to take a node. Not sure what we're calling it yet, and some sort of index or something. So just for make it smaller, let's just use an I here. All right, so let's create x.get children get at I, and this is going to be y, and that that's weird. Y is a full child of x. Create a new node and add it to x's still children. And z is going to be that one. And this is going to be y.isLeaf. And we're going to add I plus 1 z. All right. Insert the median of the full child y into x. And of course, that's going to basically be, oh, I get why it was multiplying by 2 before. Stupid question, possibly already discussed. What kind of tree was a Java tree set? Oh, I am not sure. It's been a long time since I've really looked at that. We can take a look. I mean, it's sorted. I mean, are you asking because you're not sure, or you're just testing me? Because I honestly don't know. I was trying to do this at least for the academic reason, just to implement my own B tree, so that I can better understand how it all works. Yeah, I'm not entirely sure how. I mean, it is a self-balancing tree. Yeah, I'm not too familiar with a red-black tree. I know that's an option here for the algorithm visualization. Yeah, I don't know how it works. Hmm. Oh, does this not take negatives? So it's just layered on tree map, which makes sense. Because I know that, like, yeah, makes a lot of sense. Code reuse wise. So is this going to balance eventually? I don't think this. Oh, I accidentally hit back button. I don't think that was balancing. It didn't look like it was. Oh, good, it's still there. Well, there's a little bit of balance right there. Um, oh, yeah, it just balanced. I'm not sure what the rules are for a red-black tree. Kind of interesting. Um, not sure if I want to confuse matters right now whenever I'm trying to do a bee tree. So I think that's why the degree here, instead of degree, let's just put T in our class. Because this was T times 2 minus 1. So this is basically just taking this number and multiplying it by 2. And then basically if I have 3 here, it's not really a degree at this point. If I have 3, it's actually going to put 5 objects in the each node, because it's going to be t times 2, which is 6 minus 1. So then whenever we find the median, we can just take that t minus 1. So that makes sense. I will have to run this at some point just to make sure I'm still working correctly. Just click on that. Let me see where we get. All right. No, I did the whole thing. So it did add it all in here. So there are 5 objects. It's not going to break until I put my 6th object in here. So if I add 1, for example, this time it'll hit the alternate path, trying to split it up. Oh. Oh. Did it actually work? Haha. I just haven't reorganized the data in these. Okay, so let's keep on keeping on. All right, so over here we're back at split child. We haven't finished splitting. So we need to insert the median of the full child y into x. Now we need to split apart y's keys into y and z. All right, I'm gonna have to figure out how to split this. OBS. Oh, there it is. All right, so if we have the Y children, um, splitter. Maybe split. I can't remember how to split a sublist. Duh. And we're going from T to T times 2. And Y. No. Oh, we got the other children. We needed the other keys. So this doesn't remove items, it just gives you right. But that's still copying at least all of those, right? But I need to chop off the other keys starting at T. Want to remove everything after T. I could. Does this work if I did a keys replace all? No. Basically, I need a Y get keys sublist 0 to Y or T minus 1. And this is going to be the new keys. So then Y to clear. Yeah, it's I know. I guess I could copy the other list and then just use the list and just clear it all out beforehand. That might work. We'll see. So now we need to basically do the same thing. If Y is not a leaf, let's see, you get children. Oh, let's see this up there. Okay. Let's see what that does. Does that move the children, or what's that about? Yeah. Basically, just need my keys. Nope. I just need to do that, right? Yeah. But sublist, we can do that. So T2 keys length size. One. And same thing with us. Children. So let's see this one. I'll optimize this later. Concurrent modification exception. Now, yeah, you're right. Now we'll need to new array list this. Have to copy the keys. Yeah, that might be stupid. Shouldn't that have a problem over here too? Oh, it's because Y is a leaf node. That's why I didn't have a problem with that. Alright, let me restart that, and let's see what we have here. So we have a root. It has one key, which is 5, and it has 2 children. And on the left side of 5, we have -5 and 2, and on the other right side, we have 8. We're missing 10. Where did 10 go? 5, 2, 8, 10, 5, 2. So it's children. Alright, there's 8. -5 and 2. Yeah, where'd my 10 go? Got something wrong. Well, shoot. Let's see, where did that go wrong? I mean, we didn't do this side. We found the growth subtree. Yeah, it's possible. Let's just take a look at this again. Let's just put a breakpoint here before it actually does it. All right, so here we have this root. Considered all of that as children. That doesn't seem right. I mean, technically, I guess we didn't do this side. Yeah, let's get back to that. So then insert non-full. If it's not a leaf, we need to find the other correct subtree. All right, so put the island inside of here. while I is greater than or equal to 0, and k, compared to, let's get I is less than 0. So it looks like the same loop here. Insert non-full. So it's not full. So we're just going to insert something in here. This is not a leaf. So then we're going to have to go down the other children. Yeah, I keys size is equal to, we're going to do the same thing that we did up here, t times 2 is 1. We want to split child x at I if k compared to the keys at I plus, and then insert non-full, children I. Let's see what this looks like. All right, so here, this is the first time that we're needing to do a split because the size exceeds this. So we go into a split child because the old root. So this is adding 1. Right? So we have all 5 of these. They're all in order. Now we're adding 1. All right, so let's dive into that. Step 2. All right, so y is a full child of x. So y, grab the first child of that, which is going to, so that's why the root is empty with 0 keys. That seems kind of weird, right? That's fine. Gotta have something to start with. Might readdress it later. So let's create a new node, add it to the x's list of children. All right, so we have, this is a leaf, this is a leaf. Probably need to change the status of that. But this is just splitting. This isn't promoting anything into the parent. All right, so x get children. I plus 1. So it has 1 child under here. So x is the root. We have children. We're grabbing the I plus 1, which I is 0, so that's going to get another child, z, under this. So let's go ahead and do that. So now the root has 2 children. This is the first one, the one that we already had. And then we just created a new child, which is z. Okay, so insert the median of the full child y into x. So this is y, this is x. The median will be 5. So if we... Oh, I never did remove that, did I? Did I need to remove that? Y get keys. That should have... Oh wait, this is x. So x was the root, right? So now x has 5. That doesn't seem right. I guess that is right. So that did promote the 5 into the parent. Split apart y's keys into y and z. Alright, so here we have the keys from y, and this is going to create a copy of that. And then z is going to get a sublist from t, which is going to be 3, to the end of the which I guess that's not inclusive. Sublist. Exclusive. Ah, that's my problem. It's like, where is that? So that was that. Alright, so let's stop that and restart it. Actually, I could probably just get rid of these breakpoints and take a look at the resulting collection. There we go. Alright, so this one should have... We have 5, and we have the 2 children, which is going to have -5, 2 on the left, and 8 and 10 on the right. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Or 1. I mean, that was the whole point of us breaking that apart, was for adding the 1. Alright. Let's go back in here, check it again. Oh, wait. This is the place that should have been. So this would have been adding the 1 to the new root. So why didn't that add the 1 as one of the keys in here? So let's add a breakpoint there, restart. And If we take a look at this, we have the root, we have 5, and then we have the other 4 here. So this should have added this. Let's jump into that. Step 2. Oh wait, I don't think anything ever changed. Okay, so it, X did change. So this is not a leaf. Those are both leaves. Alright, so X is the root node in this particular case. So I must have had something wrong in here. If not a leaf, find the correct subtree to answer. I don't think we're going into that point. So here, okay, that did not. Let's go back here. So it says leaf. It's not leaf. Oh, it's not a leaf. Duh. Find the correct subtree to insert the tree or the key. All right, so this is a recursive call. So here we're taking a look at this. We are going to hit play. And I is -1. And why is that? Because we are comparing, because we only had a single, so that started at 0. So then we compared to this, so K is 1, and we compared to 5. So now we're back to 0. So I is 0, right? So if the child is full, split. Oh, I don't do anything in the else. That's my problem. Is it on full? I think this needed to be out here. So this is just to find the, after we do the split, then we find the other place to put it. Alright, so let's go ahead and stop that, restart it. Just want to hit play. There we go. Alright, so now our tree, we have single key, root is 5, and then we have -5, 1, and 2 on the left side, and 8 and 10 on the right side. That seems correct. That seems correct. So then if I did a tree add 22 in here, and a tree add 42, you can probably just do these one at a time. I'm not going to spend time on creating a visualization in a toString for this. I could probably just do a toString here. Return this dot root. Oh wait, probably probably no. That's fine. What does that look like? So if I print that out, what does that look like? This will probably be non-readable. Readable breakpoints that we don't need anymore. Yeah, it's not terrible. So here's the other root node. We have one key, which is 5. We have children, which is going to be, well, yeah, it's harder to read, but it has 2 children here. Only because of the nesting. Would be nice if this were hierarchical. That's a leaf, that's a leaf. Root is not a leaf. So then it added all of those nodes to the right side. Because it's under 5, it hasn't split this one apart yet. So let's get that to split apart. Let's add a 9 in there. Let's see what that looks like. That one will stay in there because now we're at the limit now. But as soon as I add this extra one, my dog snores. 24. And this time it'll split this guy apart. And this is probably where I need to have something a little bit more legible in terms of printing. Do I really want to do a public void debug print? Let's just do a debug print. Alright, let's figure out how to do this in a nice way. So if we did a debug print here, I want to do a string builder. Might be returning a string instead of printing directly. I'm not a big fan of printing directly. I know there's probably a better way to do that now. Probably just put all of the keys here and then indent the children. And let's be append. All right. Spacer level. And then for all of the children, yeah, two string, debug print, and this is going to be +1. And the node is child. Yeah, probably hold on to that spacer. That's fine. Oh. All right. Is that gonna work? Yeah. Is that right though? Does it have 3 children? That might be true. Where did I leave off on this? So let's print that first. Probably can get rid of this print line now. I mean, I can make that a little bit nicer by putting the curly up here if it doesn't have any children. That looks correct. Oh, wait, does that have a spacer? Oh, it's because we're still doing the spacer. And it can do the same thing. I'm not writing very optimized code, but that's fine. This is just for debugging. There we go. Alright, so then whenever I add 9, that's going to split up this guy. Oh wait, no. It's going to add one more. It's not until I add this one, whenever this exceeds that limit, and it'll split. Does that look right? If I should print out the tree before and after, so that we can get a comparison before and after inserting another object. which is 21 in that particular case. So the root has 5 and 10. 5, 2. So then, yeah, you kind of have to look at it similar to how we looked at this, where the connection, the line, is going to be on the spaces in between. So we have 5 and 10 here as the key. So index 0, which is going to be the one before the 5, it's going to be all of the keys that are less than 5. Index 1 is going to be in between the 5 and the 10 here. And all of those children are between 5 and 10. And then index 1, or 2, 0, 1, and 2, is everything after 10. That seems correct. All right, so this is a B tree in a nutshell. Should be able to throw in whatever objects that we want in here, like 52. That will auto balance. There we go. Cool. We haven't done any kind of deletions or insertion or any searches or anything like that. So we should probably focus on that now. So let's take a look at a smaller grid. Let's start out with this one, right? So that's going to be this guy right here. And let's say we let's delete 10. All right, so let's implement remove. I can always do like the Java collections convention and have it return Boolean or something. Yeah, that's going to be a little bit more complicated. Should we do that? We should probably do search first. So let's do search first. This one shouldn't be too bad. So public search. We're searching for the key. Probably need to overload this because we probably want to do this in a recursive fashion. So let's do node of k equals If node is null, node is equal to root, otherwise no. That way we don't deal with a null node if somebody decides to call this directly. So while I is less than the key's size and the key compared to is greater than 0. So if so basically whenever we start at 0, keys is going to be greater than that, so that's correct. So then we're going to compare the key that we're looking at with the one that we're in, and if it's greater than 0, then we want to increment. So we haven't found it yet. So let's say that we're searching for 42. We come in here, we have I is less than the size. It's actually false because there's only one item in here. So we don't even get to the second size, but let's say that this had more than one entry, like this one down here. So we're looking for 42. So it starts out as 0, so we're looking at 0. So then we're comparing 5 with 42. Well, it is greater than, so it loops around again, and now I is 1. It is greater, well, it actually exits the loop that time because the size is exceeded, or the I has exceeded that. So we're going to look at I. So if the I is less than node get keys size, and key compared to get keys at, let's say that's equal to 0, which means that it's successful. We want to return node. Let's just make this node of k. Probably need to figure out what we're actually going to hold in these long term. But for now, let's just return the entire node. Don't know if we need to return the index or not, but Java doesn't support tuples. Else, if node is leaf, return null. I don't know if I like null. Else, let's do the recursive search. Return this dot search, starting at the key node. Or wait, sorry. Then get children, get I, and then key. There. Switch that in my head. So this will return that child, searching that child at that index. So then it'll start looking through this child, and then it'll start iterating through And once it gets here at 42, this one will kick in because it's the compare to is 0, which means that it's equal, right? 0 means that it's equal to, and then it's just going to return that node. All right, so then if I print out so this is the node that contains that particular key. I'm not sure what to do with the search on that. Might be nice to have some sort of index into it. I don't know. We'll figure out what the best approach is for that. But yeah, that's basically search in a nutshell. That one's pretty simple. Just using recursion for searching the keys. This is doing a linear search across the keys, though, basically starting at 0 and going across all of the keys. I could make this a little bit faster with some sort of binary search or something like that, because we already know that this collection is ordered. But I don't know. It really depends on how large T is. I mean, it's still going to be faster, even if we have like 1,000 nodes, 1,000 keys per node. Still beneficial to search that way. All right. Well, it is 12:12. I don't know how long I've been streaming. Probably not too long. Yeah, under 2 hours so far. What I'm going to do is take probably a 10-minute break so that I can eat some lunch, and I will be right back. All right. I went ahead and updated the stream description. I just wanted to make sure that it's fun with bee trees. So that's essentially what we're doing right now. If I ever get back to the GWT DB stuff, I'll change the stream title again. But man, 10 minutes is not a long time for a lunch break. Microwave takes quite a lot of that time. All right. So where were we? We were just searching, and we're returning a node. Maybe the node can have data. I don't know. Might yes, very. Might have some data to the other side of it. I am not sure how we're going to, because it's basically going to be a map, right? Hey, there we go. And they updated in my chat that the stream title changed. So I'm not entirely sure how to get the other data, because the whole point is whenever we start indexing these objects, we're going to want to store the person. Probably not actually store it. It'll probably just be a reference to the ID. Otherwise, might have some issues with data changing. Yeah, I'll play around with that later. Not sure what it's going to look like. I don't even know if we're going to be working on this much longer, because there's probably other mechanisms out there, like what was that, CQ something that Colin had mentioned. It might be better to use that than implementing something from scratch like this. Yeah, CQ engine. That one's pretty good. I haven't played around with it, but at least from the description of the GitHub page, it looked pretty good. Alright, so let's go ahead and print out this. We just have a bunch of numbers. And here's the organization. We have the, this is the root node. It has a single key of 5. And then we have all of the children broken down into 2 different nodes. And I want to delete or remove 10. And this is going to delete it. Probably need to have a node starting place, right? Because the root one is going to just remove root key, maybe? I'm not sure. And for the time being, let's just call this one X, this one key, rename later. So, if we're iterating through these keys, we want to iterate basically similar to what we did with the other search. It's a search, and it's basically this right here, right? So here we're just searching for the right index. If X is a leaf, meaning that there's no children to be looking at, we want to first check to see if I is less than the other size, and X, get keys. Oh, I'm spelling that out today. So let's compare this. Compare to equals 0. So this one, we found it. So this one's going to iterate until either the compare is equal or greater than 0, or we exceeded the other size of the other keys. But if X is a leaf, we also want to compare to see if it's if it is 0. I guess here we're just going to remove at I, and then I'll remove that key. I mean, this we're not going to be able to test this one easily because of the fact that we're already too deep in this tree. So let's get into the other recursion part. So if it's not a leaf, if the I, I'm gonna have a lot of potential for refactoring later. So this is basically doing the same thing. If it's a leaf, it just returns that. But if it's not a leaf and it's equal, that's whenever we probably need to handle restructuring the other table. Although we might have an issue up here if there's only a single object in there, but if it's a leaf and there's a single key in there, should probably remove that as a child too. Let's think about that and come back to it. See if there's a test case that we can use for that. If Alright, so we need to be able to delete an internal node. If we found it, we're just going to return. So private, place for that. Place for that. Looks like putting everything else. Oh. Apparently it didn't reorganize whenever I hit the key line for it. Okay, so split child, delete internal node, node okay. This is going to be the key, and then index. So here we're going to provide it the node that we're deleting out of, the object that we're going to delete, and the index that we're going to delete from that node, children or keys. So if X is a leaf, if it's a leaf and the k that compared to x.get keys get at I equals 0, then return. Otherwise, if the size. So here we're getting the children at the index I, and we're checking to see if its key count is greater than or equal to t, which is basically like half the full size. We'll probably want to delete the other predecessors at that point. Return else if the one after it is greater than or equal to t. We need to delete the successor. Else. Then we need to delete merge and delete internal node recursively. some to-dos here so I can remember. Delete is a little bit more complicated because we're having to merge structures back. So let's take a look at the delete and merge. And this is going to take a node, index I, and then another index j. So the right side node is going to be that. That's the center node. So let's add the keys. No. Gotta figure this one out. Can't remember how this works. So delete merge. Let's just do one of these at a time. So if it is a leaf, so let's search for 10. Where's delete? Or remove. So here we're starting with the root, and we're wanting to delete 10, for example. So this finds 0. And it's not a leaf. I don't think I finished this, did I? Because this particular use case isn't even in here. All right, so this use case is going to be, if this time, so we're back in the other remove. I'm jumping all over the place. I'm just trying to remember how all of this works. I have some pseudocode next to me, but I can't figure out my my chicken scratchings of my approach here. So let's do children get I, get keys, size greater than or equal to t. So what does that mean? So here we have the children, and the children in this particular case. Yeah, this is gonna fail, isn't it? No. No, this makes sense. Because 0 is on the left side of the other 5, and 1 is going to be on the right side of the 5. So we know that for every key, we're going to have that number plus 1 children underneath that that node. So in this particular case, since we have, we're trying to delete 10, um, we look at I, so we are less than size, which is 1. So then we compare 2. 10 is greater than 5. So we increment the I. X, we're still on the root node. It is not a leaf, so we jump down to here. We compare the K with the key, and if it's equal, then we want to return that one or delete that one, but it's not. So we come down to here, this else if the children at I, which I is 1 right now, it's going to be this one right here. We're looking at its keys to see if it's greater than or equal to t, which is 3, which it is. So in that particular case, we want to delete or remove. I guess I called it remove in mine. I probably need to be consistent. I think I called it delete in other places. Yeah, I need to call that remove. So we need to remove the children at index I and then K, right? So we're doing recursive, calling back to this function whenever there's enough children inside of that child. Enough keys in that child, I should say. So this is where it's going to end up coming in here. So the node X is this guy now. And in this particular case, we're iterating and we're waiting for the comparison to be greater than 0. So it's right here. So 0, 1, 2. So I is 2. X is a leaf. This is a leaf. I should probably put that in here. Yeah. Debug. Print. Oh, that's private, so it's all the way down here. The keys. Append. We have a string concatenation inside of a string builder. This is going to be node.isLeaf. That might be helpful, just to make sure that it's got the right thing. All right, so in here, this is a leaf. So we check to see if this is true. I is less than the size, which it is. We have I is 2. The key's size is 5. And then we compare at index 2. It is correct. So then we remove that key and then return. Yeah, that seems right. So this one actually should function, right? Did I print after I removed? I did not. Let's print again after we removed. There we go. Cool. So now we have 5 in that one. Yeah. So that's correct. So let's delete another one. Let's start targeting the one. So tree one. There we go. That was removed. So we remove 10 and 1. And let's remove 2. This one will probably fail. Okay. And this is only because this is where we need to do some of the merging. So it didn't actually hit anything on this side because it goes Y. Should not have hit here. All right, so we're trying to remove 10. Now we're trying to remove 1. And that's correct. And I'm assuming the other ones are going to fail. Yeah, okay. So then it gets down to here. It's probably going to try to delete an internal node. Size. So what is I? I is 0. It is less than X keys. It's 1. So then we want to delete internal node. No, because this is comparing it and it's not the same. So this one we want to recursively go in. So if I do that, no, did I not do that right? You know, let's keep implementing this and see where we come out. All right. So then else. So I don't think I need to return here. I don't think I'm going to do anything after this. I mean, I could put returned, but pointless. All right, so this one's going to be a little bit more complicated. I think it's going into this one, isn't it? For 1. I haven't finished implementation for delete internal node. So there's 10. And here's 1. It must be going to the else. Yep, that is. It's 2. Oh, I already did the one. That's right. I don't know why I kept looking at 1. All right, let's just hit play. It's the 2 that's failing. So that's going to be the else here. It's only because this has shrunk down to the point where we need to distribute. So if the I is not 0 and I plus 2 is less than the size of the children of X, and this is just making sure that if the index is 0 and the size is at least two more than the current index. If not, we need to like do delete siblings and stuff. So if the length of the children key size is greater than or equal to t, then we will delete the sibling. If the children at I plus 1 I don't know if you can hear my dog snoring on camera or on my microphone or not. It's really odd. So here we want to delete the other sibling, but the I plus 1 side. Otherwise, we need to do a delete merge on x, I, and I plus 1. So if the index is I, then we need to check to see if the children at I plus 1 keys is greater than the other t, which is our cutoff, right? It's really loud. Otherwise, delete merge. I think I need another else in here. So else if I plus 1 is equal to children size. And this is making sure that the node size is balanced. Should be remove X children get oops. There's a call. Just to go up the other parent chain. Yeah, we'll see this in action once we implement some of these. Let's do the delete sibling. I know that I keep calling it delete, but probably need to change these. I'm going to call it delete sibling, so that because all of these are in comments, I want to be able to refactor all of them. Alright, so delete sibling, we have the node x, int I, int j. So here we're going to basically remove, because this is basically just removing the range. So if I is less than j, this other stuff. So the right side node. So right node, it's going to be that one. Yeah, I originally wrote this in using arrays, so I'm having to rethink it. I'm using collections. I don't think this is going to do what I want it to do. Let's figure out where we're at in here. Because we're going to have to troubleshoot through this. Let's just build this tree so that we don't have a bunch of removes in here. So we have 5. Of course, it might balance differently if I were to do this again. 2, 1, 8, 9. So which ones did I remove? I removed 10 and 1. That time it worked. Probably because I implemented this part up here. Let's delete -5. All right, that time it removed it from there, but we actually need to remove that child too. So that's where the merge comes into play. Still have this delete sibling. Let's go ahead and those. And refactor, remove sibling. Just to make sure that we're getting. We only want to deal with the things that we're testing out. Yeah, say we have the highs. Well, that's weird. It's probably because of this. Because I haven't finished implementing this yet. All right. So I'm going to implement it like the array one. Probably need to readdress that once I remember how this worked. So right node, C node append keys of X. So then X dot get keys set I to right side node. Pop. It's going to remove the 0, right? No. It's going to remove the end. So remove the next one. Otherwise, so this one we're going to insert set. So I need to pop this one. So let's return the object that was removed. Might be it. Oh, that did some really funky stuff to my collection, but probably because we haven't removed the sibling and stuff like that. So by removing, what did we remove? We removed a 2 and the -5. Oh, we're removing that, and we're attempting to collapse this, but we just haven't got there yet. Alright, that doesn't seem right. Well, let's just keep going. Do we have any more to-dos? Yeah, we need to delete the predecessors. I mean, are we even getting to these? No, we haven't. Yeah, definitely getting here. I guess I need to do the delete or remove merge. All right, so we have the center node, which is the children at I. The j is greater than I. This is where we get the right side node. Oh, I guess I already had that down there. I think this is a index, so for int a equals 0, k plus then only because the pulling from two different spots, I actually need the index here. So let's pop. That's funny. I guess in my test, I overrode a variable that I already had. Oops. I'm not mean to hit the mic. So then, is this supposed to return something? Guess I had a mismatch of curlies. So then if the x is equal to this data root, and this is an identity equal, and the key's size is 0, this root is equal to the new node to because that's really only done here. All right. So then that is the redo merge. There's a K there. That is not right. I knew I had some mistakes in here. Too many single letter variables. So let's just go through this again. J is greater than I. Right side node is the children of J. Center node keys, we're just appending the X keys at I. And we're iterating through the keys. Then we grab the key K and add it to the other center node. If the right side node children is greater than 0, we append and then we do the pop down there. Oh, you know what? I did make a mistake. This does need to go outside. But if else and new node, we need to split that. It goes up here. New node is equal to the center node. And we're going to pop and then remove J. So now I need to figure out why this doesn't have the use. All right, so left-hand node, that J. So also J. Oh, it's because I used K or I here. This needs to be K. I should probably just. This is the key index. This needs to be outside. That's where my extra pairing fell through. And this pretty much match up. Yeah, no, duplicated. I'll refactor later. All right, let's see what that looks like. Still nowhere close. Let's implement the other spots. Let's hope for the best. Might have to go through here with a fine tooth comb. So my notes are really scattered. All right, so let's internal node. And notes ranking is to remove just for consistency. All right. Move it. Predecessor. And this is going to take X. It's just K. All right. So delete predecessor, X is leaf. We return x.get keys, get x get keys, size -1. So we just pop off the end. Oh, size. I'm using that wording. All right, so then if the children keys is greater than, then we need to delete the other sibling of x, starting with n+1, going to n, else delete merge, remove merge, I mean, and n+1. All right, and then delete, remove predecessor, x children at n. So that way, the termination of that recursion is right here at the end of pub. All right. So that was a delete predecessor. Now the successor. Successor. Okay. If X is leaf, this is our termination. Return keys. Remove at 0. If the X children get at 1, or at 1, keys. T. Wait, the sibling. Else, oops. Merge. There we go. And that's recursively removing the successors. Returns are pointless now. Only for debug breakpoints, I guess. See what this looks like. And I did something weird. I wonder if I'm just not doing the popping off correctly. Mm-hmm. So this is going to require some troubleshooting. There's a lot of state going on here. I'm assuming this is going to want to do this in the same fashion. Or if there's a better approach that I can make with this. Because here I'm just using random numbers. I mean, what would happen if I have duplicate keys? I mean, that's something that would need to be figured out. Like here, I can do 22. And both of them are in here, but whenever I do find on 22, it'll just locate the first one. If I delete, it'll just delete that first one and leave the second one. Then you would have to call delete again on the number just to delete that second one, because it's basically, once it finds it, it returns. But that's a different matter. So let's go through this again. So here's remove, and it's just going to use the root. That seem legit? Yeah, probably so. Always start at the other root. All right, so then let's go to move. I'm just comparing the code with my notes just to make sure I didn't lose something. I mean, we already know that the first couple of cases work with the remove and turn. Is that right? Well, we know that one works. Whenever it is a leaf node. So let's throw some breakpoints in here. Let's see what chaos ensues. All right, trying to delete 2. And index is 0. That's because we're going to be looking at child 1 for that 2. X is not a leaf node. So whenever I hit play, I always like putting this on the inside of the if statement, just so that I know which one it actually hit. All right, so it ignored all of those. So here we're going to check to see if the I is not 0. Well, it is 0, so that one's not the case. We're going to go into here because I is 0. So then if the children get I plus 1, which would be 1, the children, why are we doing that? I just completely hosed this up. I think I might have hosed this up. Oops. Alright, so the 0 and the length of the children at I plus 1. Oh, the keys. Alright, so let's take a look at that. So the keys here is 4. And that is greater than t because t is 3. So we're going to dive into remove sibling of x. And I is 0. J is I plus 1. And confused. All right, so here we get the C node. So I is less than J, so we will be going in here. All right, so the right node is going to be the children J, which is going to be 1. C node. I'm not entirely sure what we're doing here. C node, get keys. We're adding X keys I. So let's take a look at this. So it's adding the 5 to the C node. Does it actually remove the 2? Right? So that's what we're trying to remove here, right? Yeah, 2. So now we set X keys at I, which X is the root right now. To the right node first. So I was going to change it to 8. Yeah, I think I did this one wrong. So what it's trying to do here is it's I wish I had a way to whiteboard this. So we have 5 as the root node. We have -5 and 2 on this child, and 8, 9, 22, 42 on this node. So right now it's shifting. I don't know why it added the 5 here. It's basically taking this key, shoving it into that child, pulling the 8 out as the parent key. So once it does that, then it's still going to be balanced, but we need to remove the 8 from this side. So I think that's where I went wrong. It's right here. Because now it's just going through the other remove. So let's ignore the other breakpoints and continue on. So am I doing this wrong? That one is greater than. Let me get to that point again. I swore that would have gone in there. Alright, so right node. Oh, children. That one does not have any children, so it doesn't go in there. I missed a spot. Alright, so the length is 0. Let's ignore that side for now. So right node, get keys, remove that 0. Alright, so I'm going to restart that. That's where I went wrong. Alright, we Get back into that. So that should go over here now. Yeah. All right, so this is going to remove the 8 from the other right node. And that's correct. So if I pop over that, well, we don't have the other right node anymore, but if we take a look at the other children, we can see that the 8 was pushed into the other parent, removed from this child, whenever the other 5 went into that child. Alright, so let's I'm gonna break points and continue on. Let's see. Did we remove 2 things? And we removed -5 as well. So let's do these one at a time just to verify. So once we remove 2, what does it look like? It looks like it rebalanced because this dropped down to only a single key. So then it had to rebalance by taking this 8 and throwing it up into the other root and pushing this 5 down into that first child. Then it removed the other 2 out of here. Yeah, that looks correct. So now if I remove the -5, then it shifted the 9 up. So after it shifted the 8 up, then it had to push the 8 down into the left-hand side in order to remove the -5, because then it would have been by itself. So we have the other 5 and 8 now, and then the 9 was promoted to the other parent. Okay, cool. That works. I'm going to remove the 8 now. So this should shift things around a little bit more. Index out of bounds. No! Alright, we're back into this. Alright, I'm going to debug that. Need to get rid of all of the other breakpoints. I think this is where it failed, right? So what is X this time? X is that first child, right? Alright, so we already shifted everything around. And this is the initial removing of the 2. So this is a leaf node, and it's going in there and removing at I, which is 1. Okay. And now we are removing -5. We already shifted around the tree where 9 is the root, and we have -5, 5, 8, and 22, 42 and those siblings. And this is where we're having the other issue. So what does the tree look like right now? 9 is the root. And those are all there. So we are removing 8. So that should remove the other middle from there. It's doing something bizarre. think I have something wrong here. Wonder if it's another case where I missed some code. All right, so here let's review this. We have the center node, which is children at I. If j is greater than I. We have the right-hand node, which is the children at j. Add the keys, x, keys at I. And then we go from 0 to size of right node keys. We append. So this is where we're snagging keys out of the other one. Kind of want to see that one in action. All right. So we have the right node, C node. We're doing a remove merge. Let's just double check. So we should we have 9 there? Oh, it's because we just added that 9 to the other C node. I should have put the other breakpoint here. Let me restart that. All right. So now, if we check this, the other root is 9. And we have 5, 8, and 22, 42. And we are trying to remove I'm not sure what we're trying to remove. We're trying to remove the number 8, which is right there. All right, so basically here we're taking this key at I, which is 0, pushing it into the child, which is the C node. And now we're going from 0 to K, which is going to be the length of the right node keys. 0 to 1. So then we move the keys. Well, not move, just adding side key K. So then if the children is greater than 0, we're also going to move the other child. This isn't actually removing it, not until we get down to here. That should be fine, right? Going through 0 to the key size of the right hand side. We're only fetching. But we're not deleting anything from the R node. All right, let's try this again. All right, so here we are. Remove the 9 from the center node. So now we're going through the right side and adding those keys one by one into this. Yeah, why are we doing that? Yeah, like how did that happen? How did we get 2 here? So right hand node keys is size 2. We're not doing. Oh, I did I here. Wow. Dang. I did the same thing down here. Alright, I'm gonna skip the breakpoints and try running it again. See what happens this time. Oh boy. So it collapsed everything into a single node that time. Makes sense. Because we removed 3 things and now it can fit into a single node. So that's why we were doing that. So if I run that, removing the 2 and the -5, we're still with a tree structure, but removing one more just consolidates the whole mess. Yeah, that makes sense. I don't know what else there is on this, to be honest. Yeah, not used to the microphone being in front of me. It's weird. Yeah, I guess that's it. I mean, it might have some issues. I don't know. Yeah, let's create some tests, maybe. It's just a normal, just a main. Let me let this out. let's figure out a way to test this. So if we create, maybe we can create some nodes directly, but I think it's package private. Tree. It'd be kind of interesting to do string. I'm curious. Because of course we're not doing case insensitive. Let's just do all lowercase for now. Right. Let's print that out. Tree.debug print. Oh, it's because I'm not running the whole test. I was just running the method. Alright, so adding one more should kill it, right? Meaning it should split it apart. Split me. Or wait, we can hold up to 5. So don't split me yet. Add story time. There we go. That time it split. So story is the median. Java jumble split me is less than story, and then test and time are greater than story. Zebra. It should be in this node down here. Let's delete story. Of course, I also want to test what would happen if I try to remove something that doesn't exist. Yeah. So it rebalanced with split me on the root, and then Java jumble on the left, test time and zebra on the right hand side. It's hard to tell from this structure. I just know that this is the left hand side and this is the right hand side. So that's cool. That's really cool. I add zebra again. I'm gonna have 2 zebras in there. Or does that break? Yeah, there's 2 zebras in there. Cool. So that does work. And if we remove, let's remove something that doesn't exist. Doesn't exist. Index out of bounds. So this line right here. What about search? Does that fail? Okay, about printing. I just want to see if it throws an exception. It does not. Alright, so maybe I should print that out. Or is it returning? Is it null? Correct. And if I return node for time, okay. I mean, it has time in that node. We're gonna have to figure out how to use the search a little bit better. That's gonna work. Of course, we need to figure out that remove whenever it doesn't exist. So it's right here. So then, I mean, we gotta see if I is greater than or equal to size. Actually, the children. So if the is it possible? So just run that again. And let's put a let's go ahead and debug this, but put a breakpoint. Java exceptions. We need to throw an exception. To debug test level. Now I need to pause the breakpoints. How do I do that? I just need to pause this breakpoint until I get to here, and now I can put that breakpoint back. Because it's doing a lot of reflection and stuff. Alright, here's the out of bounds exception. And I is 2. I2. We're looking at X, and we're looking for LAK. So what's the key size? Compare to keys. Okay, is that? Why are we comparing it to those? Because it's not going to be. Shouldn't I have failed like right here? Because K. Here, let's evaluate expression. K dot compare to X dot get keys get at 0. 2. Duh. Yeah. JKL. Um, so this is where we have the issue. Because this is a leaf. But then it's also trying to get to the other children. Which aren't going to exist. I think I meant to return here. That'll fix the problem. Because if it's a leaf... Oh, I need to stop those breakpoints. If it's a... Yeah, see that? Successful. So if it's a leaf, if it has a key that matches, then we remove it. Otherwise, we just return because we went through all of the keys in the current node, which is X, and this is a leaf, so we can't go on from there. So return, that fixes that issue. So now we can't accidentally traverse down a children path that doesn't exist. All right. How are we doing on time? It is 2 o'clock. Almost 4 hours. All right, so we really have only touched the bee tree stuff. Really don't know what else to do. I mean, we can probably create like complex keys. I mean, what if we have a the ability to pass in a comparator? Because, like, for example, let's not do removes right now. Let's get rid of 2 of those, and let's just print this out. Let's see what we got. So there's that. But if I were to change this to a capital J, how will that be impacted? Yeah. It's in the same spot. Is that just a coincidence? Let's make that one capital and this one lowercase. Yeah. See, it organized jumble. Here, let me put an L in here. Or K. Maybe a K. Tree.add. Right. So jumble will be on the left of kite, and why am I thinking kite? Horse. All lowercase horse. I just want to see that the horse is in between the J's. Yeah, duh. So you can see that the J is in between. So I'm wondering if we can pass in a comparator. Because if we can pass in a comparator, then we don't necessarily have to have comparables. Alright, so then in the B tree, comparator of, okay, This is basically like half node size. We could probably make that a little bit cleaner. So that makes sure that they all go through that single constructor. Hmm. Trying to think of inheriting comparator stuff for streams. Yeah, comparator, not comparing. I don't know why I was thinking collection. So what if the should probably let me create some things in here. So let's compare with like less than or no. Yeah, less than. And then greater than. Alright, so less than. And this is going to be some key. One. Two. This one's equal 0, and this one's greater than 0. So I should be able to make greater than k, that one. Greater 2, this one, so it's equal. Only because we have the compare to and the concept of comparator just strewn throughout. There we go. Compare 2. This one's greater than key with node get keys. Just want to make sure that this still works afterwards. Almost there. Let's make sure this still functions. Yeah. All right. So this is less than. Okay. Less than. This one's greater than. And this one's equal. All right, so now we have just the other compare twos up there. And let's go ahead and run this again. Oh, my neck's starting to get stiff. All right, so that one's still fine. If I come down here, this again, let's just see, as long as the other removes still function. So that this tree, yes, it seems to have worked because we've all of those. 2, 5, 2, 5. Yeah. Oh wait. -5. I was like, no, we still have a 5 in there. Okay, so it's we removed all of these, but it shifted everything around. Okay, so that still works. Cool. Comment that out again because we are testing this. All right, so then in that particular case, if we go back to the only places that we have to compare to, I guess if the comparator, if comparator is not equal to null, return comparator compare 1 and 2. Less than 0, right? So we do that the same here. This one's going to be equal. This one's going to be greater than. So then, in that particular case, Jumble and Java should end up next to each other because of the fact that we're using a separate comparator now. There we go. So horse is on the left-hand side of Java and Jumble. Nice. So that allows us to throw in a comparator and use that. So essentially, we don't need to have this extend comparable anymore, but it would require a comparator to be passed in. I guess we can check the type if it is an instance of comparable. If I can talk, we could use that somehow. Probably something that we can play around with. Okay, see, this one's using comparables. What if we did that? Oops. Yeah, what if we did that? So instead of null here, what if we did comparator Is I looking at natural order? This one should still be the same. Dynamic test. Let's use the default constructor. Nice. So that probably does mean we can do this without comparable. So it's going to assume, I guess, the natural order comparator. Implements comparator. Comparable. Does it mean that these have to be comparables? Probably. I think this won't work unless it is, yeah, t extends comparable. So it does have to be a comparable. It's almost like I wish this would support like forcing you to use a comparator. I don't know. All right, we are at the 4-hour mark. I'm pretty sure. What I'm going to do is take a small break. I'm going to regroup and see if there's anything else that I want to do on this stream. I might start thinking about moving forward to next stream, but we'll see whenever I come back. All right, stick around. I don't know what else needs to be done with this. I did go back through these less than, greater than, equal methods and just drop it down to comparator, because now it's like you can't even get in here without, I mean, I guess if you pass a null here, you could get in here with a null comparator. I could always do option of nullable or else comparator natural order, and then we can do null here. That way we can't get in there with a null comparator. Try to not eat carrots on stream. Get a little crunchy. Yeah, so I would like to somehow figure out how to get this into the WitDB side. So it's like I need some sort of data. So right now we just have a key. We probably need to change that. That way we can actually have data with it. So this is a B-tree node. Maybe the key itself should be my own custom class. So let's do a new class called key. just for the fun of it. And that's going to implement variable of key. And let's figure that one out. So we kind of need a key. Which is a comparable. And some sort of D data. I mean, technically, this is going to be some sort of database ID, right? So this is actually pulling outside of the B tree itself. So what if yeah, let me do that. So let's just create this with a this could probably be a compound key. Yeah, I'm finally tying it back to the GWT database stuff. Hey, what do you think of the chat bubble? I think that's going to be pretty good for the YouTube side. That way, it's easier for people to follow along with without missing half the conversation on YouTube. Yeah, it actually wouldn't be that difficult, from what I can tell. This widget is actually Streamlabs widget. Might be kind of interesting to do that. Does it? Can't see what it looks like. Does it look weird like masks? It does not deal with HTML escaping very well. Comparable key of key, I think. Yeah. Yeah, I lost track of what I was trying to do. Because I'm basically wanting to hold on to some IDs. But it's gonna get weird. I don't know how to update the indexes. Yeah. Because if we take a look at the main entry point, I mean, right now, let's say that I create an index on the field's first name and age. I mean, let's go a little bit simpler and just do first name is the only field in this index. So if I create an index this way, I'm just not entirely sure, because you don't want to hold on to the data, do you? I mean, you kind of want the ID, um, and the ID should be quickly accessible. No, it's just memory right now, but eventually I'll probably have it supported for like RPC or. This is going to write on top of the B-tree stuff. Since the B-tree stuff works, I don't know if you were here whenever I was able to get that all working. B-tree says CC. Oh, and the closed caption? B-tree. Yeah. That one was a single B. E. Anyways, so I'm just not sure how to represent the other data behind the scenes. Because we could have multiple indices created on these data points. I'm just trying to think of how that would work. Because this is going deeper than I've ever bothered looking into like how databases work. The B-tree implementation that I have right now is a very generic implementation that only holds keys. But I'm going to make like a combo key that's going to contain the thing that we're comparing, the index part, the comparable, and the some sort of data point. Possibly either the object itself or the index to the object, and the indexes should already be fast. Correct. So in this particular case, it's like maybe I'm just going to have the object. Let's just do the data. No, that's stupid. Yeah, we already know that the ID is going to be on all objects in the GWT database. So let's go in here. Right now, it looks like a create index. Doesn't do anything. But let's see what we can do. I don't know why I have these carrots right next to me. I'm just going to try to eat them on stream. Alright, so let's take a look at that index real quick. I need a get fields. I'm not sure what to do on that one. I can turn off my mic while I chew. Probably in the stream soon anyways. So I'm ignoring the let's see. Or I create an index. I want to take a look at fields. Oh, never actually did anything with that one. Alright, sorry. Well, the thing is I'm not seeing it on my screen. I have to look over to the OBS side to see if there's any chat. Where's it? No, there. Right. I just haven't figured out how that's going to work. Because I was leaning towards going this direction where it's going to base it on the named properties. I don't know. Because I haven't actually implemented that side yet. Just gonna throw some code in here and see what happens. Just want to do something very similar to this. This type fields, add field, and if fields is not equal to null. A word anymore. Oh. Let's figure out how this is going to work. Wonder if I should just wonder if the data should just be done inside the index itself. Yeah, why not? So let's do stupid mic. And then whenever that finishes, I'm just going to resolve on invoke. How do you do that with a void? Right. So let's say that whenever you initialize the index, this will probably be doing some other stuff later. But now, let me hide some of this other stuff. Just for the time being. So let's say that we want to initialize with the data that's currently in there. I should probably return a promise on this. So this will be to re-index it all. All right, so adding a new property for this, so that we can put that field to the accessor for that field, so that we can call later a function get the property accessor for string game. Right. Let's figure out how to do this. So I don't even know the data type. Wonder. Because we can't have all of these named properties comparable, because we don't necessarily create indexes on every single property. Right. But that's gonna cause issues with the B tree. We need to have some sort of comparable. Correct. Correct. Yeah. I don't know what to do about that. If somebody creates an index, you create an index. I'm just trying to think of how that's going to work with the generics, because it's like from the DB to pull this up. Yeah, this is annoying. I don't want to have to do this every single time, because there's like a internal implementation versus external, but unfortunately I'm going to have to create a implementation everywhere. Right, I know that. Depends on what the IDs are, I guess. Because the IDs can be like Bob. Because these can be named keys. Doesn't necessarily have to be the old school relational database number auto increment. course, this is not going to do anything because I'm doing this index. I'm creating this index at the very beginning. I should probably create the indexes at the end just so that I don't have to do a full implementation of dealing with the indexes when adding and removing the data. And of course, I need to add the index. Let's just see what this looks like at some point. All right. So we initialize, and that's basically just going to run the initial indexing of the data that's already there. So we go through all of the name fields for this index. We grab the accessors for all of them. This is where key would come into play. I have to figure that out. So if we have field accessors, it's going to return some sort of value, but we don't necessarily know that it's comparable. Oh. Because it needs to be comparable. Gonna look like. So this does need to be comparable of key. So here we need to build the composite key. And I don't even know if that's the right approach for this. I really wasn't able to find a lot of information on how to deal with composite or complex keys in this particular way. I don't know. These kind of have to be combined So what if I did field accessors? Map. Chaining comparators. Yeah. Well, and they are going to be ordered. Right. Right. I mean, that's how that's indexed. Correct. Which makes sense. So if I got all of the field values, from all of those fields, maybe for now I'm just gonna hold the dog. Um, okay. That's interesting. That makes sense. Not really, but it's fine. Oh, that's interesting. Well, the chat comes back whenever I switch my display. Maybe I was just buffering everything up while my camera was off. Yeah, that's kind of weird. So if I did no cam, came back, it's still there. Yeah, it's interesting. I probably need to update that so that I don't know. I guess I need to do something about the chat being on the screen whenever I turn off the camera. Whenever I'm trying to eat things. I shouldn't eat on stream. Alright, so in here we have key values. So then this key, we just want to do a compare to with those object values. But we don't know what those object values are. It's like we need to check to see if they're comparable. It's a good way to do the compare to. We gotta find out if they're comparable. Oh, key values. Is there a quick way to do this? My head is pounding right now. So then I guess I gotta figure out what was first or not. I think. What's the compare to for string? Just out of curiosity. It's been a long time since I've written one of these methods. That doesn't help at all. What do you do with nulls though? Does this throw a null pointer exception? Are you supposed to throw null pointers? Just look at the interface here. Oh, okay. So it does throw a null pointer exception if the specified object is null, so that's in the contract. Good to know. So we should dereference it, I guess. I think of how to do this. Yeah, I'm not sure. Because we want to compare each one. And this is just looking at key values on this side. Most likely it's going to have the same number of key values. Some of them could be null. It's just doing one array area. We're wanting to compare both of them, right? So they're equal, yes. And now it's like, this needs to be operable. Let's do the raw types. So I'm just trying to think of, I guess if they're equal, that's when I check the second one, right? Otherwise, turn down. I mean, this will make. I mean, this is assuming that all of the other keys. This has to be a private implementation because this is making a lot of assumptions that the keys are going to have the same number of values. If they're not comparable, then it's just going to assume that they're equal and go on to the next value and compare that one. It's a big if. I might be able to, when creating the index, that might be kind of interesting. When creating the index, I could probably throw in some comparators inside of here. Just for fun. All right, so if that is that, let me go back to my index. I guess that's a D. Is that really it? Alright, does that fail? That's the good question. Alright, so let's start up the server. I don't know if this will fail or not. Alright. It's not 1,000. 8080? Stop using different ports. Okay, so let's console out the index tree, debug print. I mean, this one's not going to have anything because we're running this index before data is put in it. Okay, so let's create the index after we throw some data in it. So the first thing that I want to do, let's get rid of that. Let's bring this. Yeah, let's do that too. And let's just throw this down here. So we're creating the index after we added some objects. So it looks like let's get rid of the remove. No, that fine's not gonna work. Let's just comment that out for now. Let's say to do. Yeah, let's not remove anything right now. I want to see this in action. Yeah, kind of need a toString here. Let's put a toString in. And let's see what that looks like. So we should be adding 3 objects, is that right? Yeah, 3 rows. And we have Yeah, not very helpful. Um, Trying to figure out the correlation of this. Ooh, I just realized that it's 3:30. Um, so what order did I add them in? Justin. Let's look at the IDs. We're not looking at IDs. We're sorting by first name, right? So we have Alex, Bob, and Justin. So it looks like Alex is in the middle. Oh, it's like, why does this not look right? It's because we only have a single node. And we have 3 keys in it. We have Alex as the first one, we have Bob as the second one, and Justin as the third one. Okay, all right. Let's add some more data. This seems to be working. All right, so let's what the ID is. I'm gonna post in person. What were some of the names that I was using earlier in my test? Should probably make another instructor in here. Let's go by a little bit quicker. So we're only indexing on the first name. Just really curious, getting some more data points in here, what this is going to look like. Here, over here, refresh the browser. And we have all of these people, and you can see that whenever we do all docs, it's just returning the natural order of insertion. Right? No. Oh, it's ordered by key. That's right, or the ID by default. And that's actually correct whenever it comes to CouchDB or PouchDB. It'll actually return whenever you do all docs. It'll return ordered by the ID. But here, it's really ugly. It is really ugly, but it does look like we have this root node, and the key is Java. Person is Java null H0 undefined address, and then we have 2 children underneath that, and we have in the first child, which would come before Java, we have Alex, Bob, Jumble, Justin, Horse, That's it. And then on the right hand side of the Java key, we have the other child, which is story, test, zebra, and another zebra, because we had a zebra twice. So this is a balanced tree, and all of the nodes are in there. We have 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12, right? So we have one center and two. That doesn't seem right. How many keys do we have here? 1, 2, 3, or no, 2. Alex, Bob, and Jumble. So that's 3, 4, 5. Okay, so we have 5 in here, and that is the limit. So if we were to add one more, let's call this one Angel. Post person Angel. Right now, we are doing it case sensitive. But here you notice that this does not seem right. That does not seem right. Let me debug that. So this is in index.java. Right before do that debug print, I want to see what the index tree looks like. So under this, and index tree, which is a B tree. So we have the root node, which has 5 keys. Which is going to be Alex, Bob, Justin, Angel, and this is because of case sensitivity, because those first 3 were uppercase. And then 4, we have zebra, and then we have one child. Or wait, this is 0 children? Oh, something went awry. Is getting there? Oh, wait. 5 rows. Why do I only have 5 rows? There's my problem. I mean, it seems to have indexed properly. But why do we only have 5 rows? Did we somehow limit this to 5? Oh, you know what? It's because of my stupid index. I need to do a different strategy here, because it's not because of the fact that we're adding multiples within the same time. They're just overriding each other. That's why we have angel and zebra, it's because you're just basically clobbering each other, right? So instead of a date ID strategy, I'm just going to do like an auto increment strategy. Oh, sorry about that. I should have done this from the beginning. I mean, that's going to start with 0, but that's fine. And start with 1. And let's see if that fixed my data getting clobbered. Right, so just remove breakpoints. Okay, yeah, that's a lot better. All right, so we actually have data this time. Didn't even realize that I was overwriting all of my data. So if we look in here, it's really hard to tell, but it does look like we have 3 children underneath this. Kind of need this to not word wrap. We do the E without the doc. Because we only really care about the keys, right? That might actually help quite a bit. Yeah, here we go. That's a lot better. So in the root node, we have Angel and Story. On the left of Angel, we have Alex, Bob, Jumble, and Justin. On the right-hand side, like in between Angel and Story, we have Horse, Java, Split Me. And then on the right-hand side of Story, we have Test, Time, Zebra, and another Zebra. So that actually did index pretty well. Yeah, I'll definitely need to in my tasks. Let's take a look at those, and we probably need to start thinking about wrapping up the stream. So we did this mostly. So we will need to probably, well, let me take that back. We implemented a B tree, but we need to so basically for the create and delete, create, update, and delete, create, update, and delete, no indexing on read. We do the indexing at the time of adding the index of the data that's already there, but we don't have anything that re-indexes whenever you add a new object into the other collection. And then whenever we update objects, that one's going to be interesting as well, because then we would have to just check to see if the key was modified. So it's like we need to remove the node from the index with the old data before the new data. But how do you do that? That one's going to be a difficult one because we're not actually copying the records right now. If we were copying the records using like the WitRPC stuff, then it would be easy, because then we could just look in the local store and know that nobody has modified it outside of this process of storing through the database. But if we're actually mutating the objects behind closed curtains, then we have a problem. I don't think I'm actually doing any kind of updates in here. So that's something that we're going to have to figure out, the continual indexing. There was something else that I was planning on doing. We need to tie in search. Yeah. And what else? It's probably good for this. I mean, right now we're just holding onto the entire document in the index. I mean, it's actually the same object, so it's not like we're making copies of it and killing the heap. But at some point, we're probably going to change it so that this key will just retain, instead of the document, it would just retain the document ID, so that we would be able to look up the ID fairly quickly. Because that's all an index is. It's just a layer on top of the database with a different, narrower search scope. And that's what we're trying to achieve here. So in the next stream, since I'm going to be wrapping it up for today, I'm going to allow it to do the continual indexing and to figure out what to do on delete, or not delete, but update. Update's going to be the hard one. So maybe I'll just deal with the create and delete for now, but I really don't know what to do about update. Yeah, so we have plenty to do in the next stream, so I'm going to call it for today. I appreciate everybody that came out, and for everybody that's on YouTube. Expect another one of these within the next week or so. Otherwise, I will see you next week. I believe that Colin might be streaming tomorrow. He was unable to stream on Wednesday this week because of other projects that are going on, but if not, yeah, he's gonna try anyway. But if not, we'll see you guys next week. Take it easy.